This is Score Group's MIDAS meter. It's a valve leak detection, quantification and trending tool that's been developed over 40 years of research into acoustic emissions and their correlation to through valve leakage. The technology used allows us to non-invasively measure valve sealing performance, whilst the valve is still installed in the process line, making it safe, fast and easy to use. With hundreds of these devices now in service in over 30 countries around the world, supporting intelligent valve management contracts, this is the go-to device for non-invasive, in-line valve sealing performance monitoring. MIDAS meter can be used on any valve that has an isolating capability. That includes valve design types such as ball, gate, globe, check, butterfly, needle, pressure relief, plug, diaphragm, and any other isolating valves. There are 4 levels of value that Score Group's MIDAS meter non-invasive testing technology delivers. These are through valve leak detection, through valve leak rate quantification, through valve leak rate trending, and intelligent valve management support. As long as the valve being surveyed is in the fully closed position with a differential pressure over 1 bar across its seats, then MIDAS meter can be used to survey performance and deliver quantifiable value. To demonstrate how MIDAS meter works, we built this neat little demonstration panel. It's a manifold system, so let me explain what we've got here. On the upstream side, we have an air inlet. We have about 5 bar differential pressure. From the upstream, across these 5 valves, leading to the downstream and out through the flow meter. So as we can see at the moment, the flow meter is not reading any leakage. In order to simulate some leakage, I'm going to open one of the valves very slightly, and then we'll see some leakage coming through the flow meter. So if we look at the flow meter here, you can see there is now some leakage coming through one of those valves. Our challenge here, of course, is that we don't know which valve is leaking. If you imagine a larger process, there could be many hundreds or many thousands of valves, all pointing at the same manifold outlet. So it's important that we have a tool that will detect which of these valves is leaking. In this exact scenario here, if we can't differentiate between which valve is leaking and which isn't, we're going to have to remove 5 valves, do 5 repairs, use 5 spares kits. It's going to take 5 times as long, and it's really inefficient. If we could establish which one valve was leaking, it would allow us to immediately make 80% savings on our maintenance budget. So that's what we're going to use MIDAS meter for. The good news is it's going to take you about 30 seconds to learn how to correctly use the handset device to find the leaking valve. We said that level 1 of added value comes from MIDAS meter quickly, easily and non-invasively finding through valve leaks. This is sometimes referred to simply as troubleshooting. So let's show you how this device finds the leaking valve. 4 valves in the fully closed position, 1 valve partially open to simulate the leak. We're now going to proceed, switch on our MIDAS meter handset using the big yellow button. Runs through a sequence, on, B and a number tells you the battery life, and then it drops to a 2-digit number. In this case, we have 21 decibels. 21 decibels of noise is your background noise. What we will do on the demo panel is look for additional decibels of noise. That's what's going to show you which valve is leaking. So the first thing to say here is each of our valves have been numbered. You can see the serial numbers TV00, 2, 3, 4 and 5. To survey each valve, we're going to place a little bit of silicon couplant, about the size of half a pea, split pea, onto the sensor and then hold it in direct surface contact with the body of each valve individually. What you'll see on each of the valves is that we'll have additional decibels. In this one we have 36 decibels. I'm just going to move now to number 2. Give that a few seconds to stabilize. We've gone from 32 up to 40 decibels on valve number 2. Let's move to valve number 3. We're now up at 61 decibels and static at 61. Move to valve number 4. Numbers rising and stabilized at 40. And finally, the 5th valve, body reading. Stabilized also at 40 decibels. So based on our survey readings for each of those 5 valves, valve number 3 had the highest stable reading, and so that is our valve that is leaking. The noise you're seeing in the other 4 valves is effectively spreading through the pipework to reach each of the other positions. The source of the highest decibels is where your leaking valve is. So in order to prove this is correct, what I'm going to do is I'm going to spin round the demonstration panel and we'll have a look in behind to see the leaking valve. So you'll see one of the hand levers is turned and we'll look directly up the end of the panel. As you can see, it's valve number 3 where the hand lever has been marginally turned, and that is indeed a leaking valve. You may also be able to hear the air escaping from the outlet of the flow meter. If I fully close that valve, you'll hear the noise goes away, as has the leak. And we can demonstrate that by showing you the flow meter reading 0 and the decibels on the valve, which we'll do right now. So we can see here, no more flow coming through the flow meter. We still have pressure, of course. Valve is now in the fully closed position. If we come on with our MIDAS meter, you can see we're back down at a background reading. In this case, just a couple of decibels above what we'd call our 0 reading of 21. We're sitting at 23 decibels here. And all of the valves will be at the same level or thereabouts because we've taken away the leak. The noise that you were seeing in the other valves was only generated because it was sound spill from the leak source. In other words, the sound was attenuating across the whole panel, and so you saw other readings in other valves. Those readings are all now gone, and so we know that we've repaired the leak satisfactorily. In operational terms, this is a good way of demonstrating that leaks have been correctly repaired. So, what we've been able to demonstrate successfully there is that literally with just a few seconds worth of training, we can use this completely non-invasive MIDAS meter survey method to correctly identify leaking valves. Following on from this, I can now show you that we can also use MIDAS meter as an effective maintenance verification tool. If I simulate the maintenance or repair activity by closing valve number 3 as I did there, place the sensor back onto the body, you saw that the decibels we measured previously are now all gone. In summary, MIDAS meter troubleshooting surveys moves us towards value-based maintenance. That's the 80% savings I spoke about, where we leave the 4 valves that are okay alone and we only repair the 1 leaking valve. In part 1, we used MIDAS meter for positively identifying through valve leaks, troubleshooting, as we called it. In part 2, we're going to focus on the higher value proposition of leak rate quantification. This is really important because you're not going to try and stop your process production every time you find a tiny leak. With this technology, you'll want to take a top-down approach to maintenance resources deployment, where you start by fixing the biggest leaks first. In order to inform that decision-making process, you must be able to quantify all through-valve leaks. What we're now going to show this time is not just the readings on the LCD screen here, but we're going to capture decibel readings at key positions and do a complete survey so that we can then quantify the through-valve leak rate and compare that to an allowable leak rate for that valve asset. The conditions for surveying a valve are consistent. We need the valve to be in the closed position with a differential pressure of at least 1 bar, preferably higher, and we need to know what the process fluid is, for example, liquid or gas or steam. The decibel readings taken by the MIDAS meter handset are going to be sent wirelessly to the supporting smartphone device, where we've also entered some basic details such as valve type, bore size and pressure class. So you can see we've set our target valve up in the system already. It's valve number 3 on our demo panel here, tag number TV003. We're now going to run through the test as guided by the automated software routing. First, I will press on valve number 3. You can see new survey has popped up, so we'll select new survey. The MIDAS meter is switched on and we want to add a new survey, so we click yes, and it will now make a link directly to the MIDAS meter. In this case, we're using MIDAS meter with serial number 0128 at the end. It's in calibration. It's a blue box. If the device goes out of calibration, that box will turn red. So that protects you against using an out of calibration device. So let's select our MIDAS meter. Establishes the link. The first thing you will see is that our live reading on the MIDAS meter handset is now replicated at the top of our smartphone software. To complete the survey, we're going to take readings at 5 key positions. So let me first point out those 5 positions. We start on the upstream side of the valve at the upstream far position. We then move to upstream near. Because this is a small valve, we only need 1 reading on the valve body, which we'll take directly as we did before in troubleshooting. Then we'll take 1 reading downstream near, and our final reading will be taken at downstream far. In each case, we're still going to want to use a little bit of silicon to give us that good coupling and a nice clean reading. To make this nice and easy for the user, the software is designed to talk you through the survey at each stage. It will tell you where to take the reading and how many readings to take. The way we activate that is to click on Route. So you can see here all of the positions I described, and at the bottom, Begin. So I've now clicked Begin. The first reading it asks for is background, and it tells me I want 1 reading. The background reading is essentially taken in air to verify that the sensor is working fine. So we should see 21 plus or minus 1 decibel if the sensor is working correctly, and in this case it is. The switch at the front has an H and an S. H is for hold, S is for send. Because we're happy with 21 decibels, at the background position, I can now press send. You hear the noise, it's transferred those 21 decibels into that background position with a time and date stamp. The red text previously is now green, indicating that we have the correct number of readings at that location. I then want to hold the H button for 4 seconds you'll hear a new noise. It's moved to the next position. So we can now see that it's looking for at least one reading at the upstream far position. So let's take our reading off this nice flat fitting here. Again, place the sensor on, hold it nice and steady, wait for the number to stabilize. 28 decibels is stable. I can now send that over. Again, all our text has gone green, indicating we have the correct number of readings. I press H again to move to the next position. We now want to take the reading at upstream near. So upstream near. You can see as we move closer towards the sound source, the decibels are increasing. Just let it stabilize there. We capture 39 there. Again, you can see the captured number 39, everything's gone green. Move to the next position with H. It's now looking for at least one reading on the valve body, so there's some silicon there already. Let's just go straight on. Stable at 53 decibels, we'll capture that. H, move to the next position. Downstream near, use a little bit more couplant because we've not got any on there. Again, all the time you can see the number live on the smartphone screen as well. Quite stable at 37, 38. Jog forward one more time to the downstream far position. This will be our last reading in the survey. You can see we've already lost a lot of decibels just in a short space of distance. And we'll capture that at 25. So, H one more time completes our survey. You hear a double beep. You can now see that we also have at the bottom of the screen a button for pressures. We need to tell the system how many bars of pressure we have differential across that one valve. So if we look up at our pressure gauge, you can see that's about 4.5 bar. So I click pressures. I'm going to type in on the upstream side 4.5, and on the downstream side we're coming out through the flow meter to atmosphere, so I'm going to put 0 there. Click update, get rid of the keyboard. So we now have a complete survey, and you can see that my analyze button, which was grey before, is now dark blue. It's activated, and we're ready to conclude the survey and do the calculated leak rate. So I'm going to press that, and here is our calculated leak rate. So in this case, we've measured 11.2 litres per minute of leakage coming through that valve based on the decibel readings that we were able to capture, the differential pressure, and the fluid type. If we scroll to the bottom of this screen, you'll see some valve details, but you'll also see the allowable leak rate for this valve was set at 5 litres per minute. So at 11.2, we're more than 2 times the allowable leak rate. So we have a red traffic light indicating that we want to do some repair or maintenance, or maybe even replace that valve. So you can see from our demonstration, a complete survey will typically take around 2 to 3 minutes on a valve, up to around 6-inch bore. Although that could be longer, up to around 15 minutes for the largest valves in your population. That's because on larger valves, we take multiple readings on the valve body, all around the circumference of the body, to make sure that we capture that highest stable reading. You should bear in mind that the typical alternative valve leak test techniques like pressure build-up or pressure area tests are very expensive and very time-consuming. One of our customers advised me that it takes on average $3 to $5 million to run pressure build-up tests on emergency shutdown valves on an offshore oil rig. Imagine using MIDAS meter, just exactly as I've demonstrated here, to non-invasively survey those valves in situ, and then report the through valve leak rate in a matter of minutes. thus saving the $3 to $5 million and returning that to the bottom line of your accounts as profit. All MIDAS meter survey results are stored for immediate reporting after testing, speeding up and focusing the decision-making process for valve maintenance or replacement planning. A further press of the back arrow on the smartphone device takes you back to the main navigation screen that allows you to then select reports. We shall cover report types, data management and valve management optimization in the next video. In summary, MIDAS meter therefore removes all guesswork and focuses all remedial actions to deliver best return on investment of maintenance resources. This is particularly valuable